Should I try to share my screen to present the slides?
Yeah, please. And try.
Okay.
Yeah, we can see your slides.
Perfect. Still hear me? Yeah.
Just a moment. I guess we should wait just 1 minute and start.
Yeah, perfect.
Okay, dear colleagues, it's a great pleasure to introduce Fabian Pedregosa from Google. Fabian is outstanding person. For example, he has at the moment for about 70,000 citation at Google Scholar. It's outstanding result, I guess. So recent interest to accelerated method. I guess this is very important direction, and Fabian has several papers in this direction around acceleration and precise estimates of rate of convergence of different algorithms. And today, as far as I understand, we know something about super acceleration, and in my opinion, this is very interesting. And I hope you enjoy this talk. Please, Fabian, you can start.
Great. Thanks a lot, Alexander, for the very kind introduction. So yeah, let's get started. Just for a bit of context, I want to talk first about the heavy ball method, or gradient descent with momentum, which is a method that I'm sure you all know well. So this is a method that has two parameters, a step size that I'm going to denote h, and a momentum parameter that I'm going to denote m, where the momentum is something between 0 and 1, and the step size is something positive. The heavy ball method has a recurrence like this, where the next iterate is given by the previous one, plus the momentum parameter times the difference between the previous two iterates, minus step size times the gradient. And we know a lot about this method. We know, for example, that is asymptotically optimal among gradient-based methods on quadratic objectives. But perhaps the reason why there's been a surge in interest in recent years in this method is not because of this acceleration property, but because it's one of the main methods used in deep learning. So more precisely, it's a stochastic variant of this method where the gradient is replaced by a stochastic estimator of the gradient. Okay. And the method that I want to talk about today is a much more recent twist on the classical heavy ball method. and I'm going to call it a cyclical heavy ball. So here, instead of having just one step size as before, we're going to have two different step sizes. Then I'm denoting H0 and H1. And the method alternates between these two step sizes. So now the recurrence is, as before, it's given by the previous iterate plus momentum times the difference of the two iterates. But now the step size is going to change. And for even iteration numbers, it's going to be one thing, H0, and for odd iteration numbers, it's going to be another thing, H1. So if H0 and H1 are the same, this becomes the same method as before. But if they're different, then it leads to a different method. By the way, feel free to ask questions and interrupt me at any time. And so one of the reasons why we're interested in this method is because a few years ago, around 2017, some people suggested to use this method in the context of deep learning and showing that it was giving better results than the classical heavy ball method. And nowadays, it's become really popular. It's really pervasive in almost any deep learning framework. You're going to find this method. So I found it in TensorFlow, PyTorch, Optax. Basically, any one of the big deep learning libraries have support for this method. But so far, there's no, as far as I know, there's no analysis that explains why this cyclical choice of step sizes might accelerate or might give better in some sense performance than the classical heavy ball method. So before getting into the theory, if you just try to run this cyclical heavy ball method on some toy problems like a quadratic problems or logistic regression problem, and you cross-validate both step sizes, you'd likely find some figures like this. By the way, I'm calling Polyak heavy ball as just the heavy ball method with optimal parameters. Okay, so if you run these two methods side by side, you'll probably find something like this, where actually the cyclical one gives a faster convergence. Here I'm plotting iteration numbers and the norm of the gradient. So this means that the cyclical heavy ball is a bit faster. Now this raises a lot of questions. So for example, for the classical heavy ball method with optimal parameters, we know that the slope of this curve, the rate of convergence, is given by this quantity that depends on the square root of the largest and smallest eigenvalue of the Hessian. And we know that this is, as I said, this should be optimal among quadratics and first order methods. So then this raises the question, then if this is optimal, what is the slope here of the cyclical heavy ball, which seems to be faster than that of classical heavy ball? And also, what does it depend on? Is it, for the classical heavy ball, it depends only on the largest and smallest singular value. Is it the same for the cyclical method, or it depends on other quantities? And as we'll see, it will depend on other quantities. So that's going to be what I'm exploring today. Lots of questions and hopefully also some answers. So the outline of the rest of the talk is the following. The proof technique that I used is based on a connection between optimization methods and polynomials. So I'm going to talk a bit about this proof technique, and mostly applied to classical methods. And then in the second part, I'm going to apply this proof technique that I just introduced to this new method, to the classical heavy ball. And at the end, I'm going to finish with some empirical results and also open problems. Okay, so let me tell you a bit more about this connection between optimization and polynomials. This is a very classical, classical proof technique. So if you go back in time to the 50s, most of the work there, like people working on conjugate gradient, this kind of stuff, they were using this thing all the time. One of the issues is that it doesn't really generalize beyond quadratics. So it's sort of fell out of fashion in recent years. But I really like this proof technique because it gives rise to I think, a lot of insight. Two very elegant proofs, very succinct proofs, and the reason for this is that, well, by making the link between optimization method and polynomials, we can use some results from the theory of orthogonal polynomials that, as you know, is a very old theory and has been very refined by now. So let's see what I mean by this through an example. So let's start simple. Let's start with gradient descent. Okay, consider gradient descent on this quadratic objective function, where the optimum here is at x star and the Hessian is this H matrix. So here the gradient of f is just h times x minus x star. So if I write one step of this iteration, I get this expression that I can factor also in this form. So this is nice because then it gives us a recurrence where you only have on one side xt minus 1 and on the other side xt. So you can repeat that t times until you reach iteration 0. And now if you do that, what you find is that you get the difference between iteration xt minus 1 and x star, so the error that you have. You can express it as some polynomial in the matrix H in the Hessian. So here, this is a kind of in factored form, but if you expand this expression, it's going to be a polynomial in the matrix H times the error that you had at initialization. Okay. So this is still, I mean, from this you can already say some things. For example, you can say derive step sizes for which it's going to converge, because we know that the spectral norm of this needs to be smaller than 1. We can see already some stuff, but still we have a polynomial that's polynomial in a matrix H. Ideally, we'll want something that's polynomial in a real variable, which is where we have the most extensive theory. And we can get that fairly easily. So just from the previous expression, taking norms on both sides and then applying Cauchy-Schwarz, we get this expression where on one side we have the error at initialization, and on the other side, the 2 norm of this polynomial. So just by definition of the matrix 2 norm, the matrix 2 norm is the largest eigenvalue. So we can rewrite this now as the maximum of this expression, which now is a real valued polynomial, is no longer a matrix polynomial. Okay. And so in this case, because this is a pretty simple polynomial, the 1 minus 2 L plus mu lambda to the power t. This is pretty simple. The plot is on the right side. So you see that it's a polynomial that has a root, when lambda is 1 over lambda is L plus 1 divided by 2. And after that, it's just increasing. So we can see fairly easily that the maximum of this polynomial is going to be on the edges, right? So we can compute this, in this case, we can compute this maximum exactly. And we get the familiar convergence rate of gradient descent, L minus mu divided by L plus mu to the power t. Okay, by the way, across the talk, I'm denoting L and mu by the largest and smallest eigenvalue of H. And I'm also going to call the residual polynomial this quantity that appears inside the max. Okay. I don't know if there are any questions until now. Feel free to ask anytime.
What is the picture?
Okay, so what's interesting about these proof techniques that I just showed for gradient descent is that it extends beyond gradient descent and basically to any gradient-based method. So by gradient-based method, I mean anything in which the update is given by a linear combination of the gradients. So a very classical result is this one that says that for any of these gradient-based methods, we can associate a polynomial that I'm calling the residual polynomial, such that we have this bound on the error at iteration t. So what this means is that we can decompose the error at iteration t by the max of this polynomial. So here the problem difficulty enters through this max. So note that the max is over all elements in this interval that contains all the eigenvalues of the Hessian. So, for well-conditioned problems, mu is going to be close to L, so the interval is going to be something far away from 0 and small. For ill-conditioned problems, mu is going to be close to 0, and we're going to have an interval that is where the mu is close to 0. And so the other key element of this decomposition is the algorithm that enters through the polynomial PT. So this is what I call the residual polynomial. And one thing to know about this polynomial is that it always satisfies this constraint that it's 1 at 0. So because if it didn't satisfy this, for example, you can select the polynomial equals to 0, and then you would have immediately zero error. So of course, the game is going to be to select polynomials that verify these constraints but are small, because to achieve a small error, you require the max of this polynomial to be small. Okay. So one thing I really like about this result is that you can go both ways. So you can start from an optimization method, find its polynomial, and then this equation is going to give you a convergence rate. But you can also go in the other direction. You can start from a polynomial. Suppose you find a polynomial that has a very small maximum value, for example. That gives you a convergence rate, and then you can reverse engineer the optimization method from this polynomial. One thing that I won't talk much about in this talk, but I wanted to mention anyway, is that this same technique of pairing optimization methods with polynomials is also very useful in the context of average case analysis. So for example, all that I said before is for worst case analysis, because I was taking bounds when I was bounding the error. But instead of taking inequalities, you could, for example, take expectations over a class of problems. And if you do that, then you get a similar expression as before, except instead of max, now there's an integral of the same polynomial. And the problem difficulty, instead of entering through the max, it enters through this quantity d mu, which represents the density of eigenvalues for this problem class. So for example, for things like deep neural nets, we know that a reasonable choice for this density of eigenvalues is the Marchenko-Pasteur distribution. It's not exactly the same, but it does model a large part of the eigenvalues. And so, for example, plugging in the Marchenko-Pasteur distribution here, you can get an analysis for optimization methods in the average case across a family of functions that includes, for example, least squares with random data. And I've done a couple of works on that. So one work was on driving accelerated methods, so trying to find what's the optimal polynomial when you have as d mu, for example, this Marchenko-Pasteur distribution. The other one is in concentration, also looking what happens when the size of your problem grows and your number of samples grows. There's some concentration that appears, meaning that although the problem still has a lot of randomness, the eigenvalues actually are not random anymore in the limit. And so the halting time, so the time it takes to solve a given problem, becomes deterministic. So yeah, that's another thing where this polynomial framework helps. So okay, I'm going to come back to the heavy ball method and our worst case analysis. So here what I want to show is how to apply this polynomial formalism to the analysis of the classical heavy ball method. So as I said before, the heavy ball update has this form, and although I'm not going to show it, the residual polynomial that's associated with this method is this expression for PT. So here what's important to notice is that this polynomial has a term where the momentum appears, a momentum like square root of momentum to the power of t. And then this is multiplied by a convex combination of two Chebychev polynomials, a Chebychev polynomial of the first kind and Chebychev polynomial of the second kind. So this is handy because we know a lot about Chebychev polynomials. We know a lot, especially about the extremal properties of it, Chebychev polynomials. So if you remember, the rate of convergence was going to be the max of this polynomial PT. So thanks to this expression, we're going to be able to find what this max is. On the right-hand side, this is a plot of both the residual polynomial associated with gradient ascent and with this with the heavy ball. And as you can see, it goes as expected, I guess. It decreases faster than pure gradient descent, and you also see that it has much more oscillations than gradient descent, which is kind of expected because gradient descent, the residual polynomial only has one root in the middle, while we know that Chebychev polynomials have roots that are distributed across the whole interval of convergence. And another important fact about this expression is that Chebychev polynomials are not evaluated directly at the argument. So if you remember, usually Chebychev polynomials are defined to be in the interval -1, 1, while the interval we actually care about is usually mu L, so the interval where eigenvalues live. So what we do is to shift those intervals. So this is exactly what this sigma function is. This is a linear function that is shifting the original argument by some quantity that depends on the step size and the momentum. And we'll see more about that in a few slides. Okay. So as I said, our goal is to find the convergent rate of the heavy ball method. And for that, because we have an expression in terms of Chebychev polynomials, we need to understand a bit better how Chebychev polynomials behave. So the key fact that was known for a very long time is that in the -1, 1 interval, Chebychev polynomials are very well behaved. In particular, they are bounded either by 1 for Chebychev of the first kind or by t+1 for Chebychevs of the second kind. So this is a very low bound, especially considering that outside of the -1, 1 interval, they grow exponentially because they have this. So Chebychev polynomials admit this explicit expression where you can see that one of these two terms is always going to be greater than 1, and because of the power t, it just grows exponentially. Okay, so since our goal is to have a polynomial that is small, we'll always want to be our polynomial to be evaluated in this -1, 1 interval. Okay, so I'm talking a lot about the -1, 1 interval and the eigenvalue interval. These two are related through this link function. So as I said, our goal is that our eigenvalues are always in the -1, 1 interval. So one way, equivalent way to say this is that the pre-image of this function is always in the -1, 1 interval. So this, if we compute the pre-image of this link function, this gives us conditions on mu and h to verify this, that the pre-image is in the -1, 1 interval. And one expression that I'm going to use from now on is that of the robust region. So the robust region are parameters, or like the set of parameters for which the image, the pre-image of this function is, sorry, the image of the link function is in the -1, 1 interval. Okay, so intuitively, this just means the set of parameters for which the kind of the link function is well behaved. Okay, and that's where, of course, we're going to get the best convergence rates. So one thing we can do also to get more intuition about this robust region is to plot it. So for example, you can take momentum parameter and step size and plot what is the region the set of momentum and step size parameters that verify the condition that I just said, and you'll find that it's a region like this in the plane. So one interesting thing about this region, because I said that Chebychev polynomials are bounded in this region, is that if you look at the expression for the residual polynomial, if the Chebychev polynomials are bounded, this means that the rate is only going to depend on this this first term that is exponential in t. In other words, the convergent rate here only depends on the momentum parameter. This to me seems a bit magical. I'm not saying it's new. It's a well-known fact, but still I think pretty interesting that inside this region, the only thing that determines convergence is the momentum parameter and not the step size. Okay, I'm going to stop just a second to see if anyone has questions about this. Okay. So yeah, one of the key takeaways from this slide is that the asymptotic rate in this region is given by the square root of the momentum. So clearly, we're going to want to achieve the best rate, we want the momentum parameter to be as small as possible, while of course staying in this region. And figuring out from the previous inequalities how small can the momentum parameter be, you reach this, which is the familiar expression of Polyak momentum.
It seems that question appears. Elnur,
yeah.
could you ask your question?
Sure.
Hello, can you hear me?
Yeah.
So, hello. My question is, as far as I understand, small m's are not allowed here. Do you have any intuition why is it so? Am I clear?
Yeah. So they're not allowed in the sense that if small m's take you outside of this robust region, I don't know if I have a good intuition. To me, it would just not be fair if you could take smaller m, because your convergence rate is given by square root of m. So it's clear you could not just take it arbitrarily slow, otherwise you could converge arbitrarily fast. And let's see, another way to see it, maybe from the link function. I'm thinking what happens if on the preimage, if you take m to be really, really small. Yeah, okay, right. So okay, so coming back to the link function, you want the preimage, well, you want the eigenvalues to be contained in the preimage, and if you take m to be really small, you're kind of decreasing a lot this interval, which means that at some point it's just not going to contain your eigenvalues. So your eigenvalues are going to overflow, and you're going to be in the region where the Chebychev polynomials explode.
Is it true that if m is 0, then this method contracts, reduces to GD?
Yeah, absolutely. So the robust region would contract. Yeah, totally. Which I guess explains why in gradient descent you don't have this free lunch in which your convergence doesn't depend on the step size, right? Gradient descent, your convergence always depends on the step size.
Okay, thank you.
Yeah, thanks for the question. Okay, right. So I was saying that from the inequalities of the robust region, minimizing m, you recover this choices for m and h. And as I said, from there, it's trivial to derive the asymptotic rate because it's just square root of m, and we recover the classical accelerated rate for heavy ball. Okay, so that was it for the classical heavy ball. Now I'm going to try to apply these techniques to, that was it for the classical heavy ball, and now I'm going to apply these techniques to the cyclical heavy ball method. So just as a reminder, the cyclical heavy-ball method is the same as the classical one, except now the step size is going to change depending on iteration number. The momentum is not, the momentum is constant. I could vary it, but we've found out that it actually doesn't really add anything to vary the momentum parameter. So I'm just going to consider for now the method in which only the step size varies. Okay. Now, if we try to derive the same analysis as before for the cyclical heavy ball method, we fall into a roadblock. So this roadblock is because the analysis that I was doing before kind of crucially relies on the polynomials. Orthogonal polynomials have a nice recurrent in which you can express the next polynomial of next degree in function of the last two. So this is still the case here, except now the coefficients are going to depend on the iteration number. So because my step size changes across iterations, now this recurrence is going to have coefficients that also change through the iterations. And so if I try to do the same proof technique as before, it just doesn't work. It doesn't go through. Now, one thing I realized as I was working on this is that people in the field of orthogonal polynomials have actually looked already into the problem of this kind of polynomials where the recurrence depends on the iteration number. And they call it orthogonal polynomials with varying coefficients. And it's something that has been studied. I think one of the first works was Theodore Shihara in 1968, and then much stronger results on the asymptotics and also mostly on the asymptotics by Van Asche in the 80s. And so there's a mature theory on this class of problems. And reading on this, I realized that actually the way to analyze it is pretty straightforward. Instead of trying to analyze as we usually do in optimization, iteration by iteration, so trying to have a bound on xt, the key idea is just to chain iterations and not have a bound on xt, but rather have a bound on x2t, so on all even iterations, for example. And if you do that, then you can have a recurrence. So here, for example, I have a recurrence in which I'm expressing the polynomial after two iterations in terms of the polynomial at the current iteration and the polynomial two iterations ago. And if you do that, well, there's still h0 and h1, but it doesn't depend on t anymore. Okay, it's a slightly different recurrence, but you do get a recurrence that does not depend on the iteration number as long as you jump by two iterations at a time. And now using this fact that now I have a recurrence, I can do as before and associate or rewrite this polynomial in terms of Chebychev polynomials. And the result was kind of surprising for me, is that if you do that, you get something that is basically the same thing that you had before. So I don't think I'm going to compare it, but this expression is the same one I was showing before for the Polyak heavy ball method, except now the link function is very different. Okay, before it was just a linear function. Now it's a square root of a quadratic function. But I still have, the Stepsize of the first kind, the Stepsize of the second one, even the terms that they're multiplying are the same. And I also have, very importantly, momentum to the power t that appears at the beginning. So before I had, I think, t divided by 2. Here I have t. That's just because I'm rewriting the iteration number as 2t because I'm jumping one iteration. But it's really the same thing. The only thing that changes is the link function. Okay. So, however, one thing changed with respect to the previous one is that the previous one was a linear function. So, if your eigenvalues are real, the image of a linear function on a real function is a real function. Now, however, I have this square root of a quadratic function, and now suddenly things can become complex. So now I need to start worrying about, well, what happens Chebychev polynomials when they're evaluated at a complex number. Actually, I think someone was telling me the other day that it's either real or pure imaginary. It's not, so it's a very specific of kind of complex number. But still, the point is that you can be evaluated at imaginary numbers. So now we need to worry a bit about, well, what happens when you evaluate Chebychev polynomials in imaginary numbers. So it turns out that basically the same results hold as before. Chebychev polynomials do grow exponentially as before everywhere except on the -1, 1 interval. So they're going to have all the roots in that small segment of the real line, and outside of that small segment, they grow exponentially. Okay, so unfortunately, we're not going to have any region of the complex plane where Chebychev, doesn't grow exponentially, except for the one we already knew. So now let's take a closer look at this link function. Now that we established that, well, we're not really that interested into complex numbers, but we're still interested in values, preimage, the preimage of this link function that leads to real values. So one thing we see is that, well, before the link function, like the image of the link function or its preimage is an interval, right? The image of an interval is an interval, but that's no longer true now. So now what can happen is that the preimage of this function is actually a union of two intervals, because you're taking the square root of a quadratic, and wherever this quadratic is negative, well, that's a complex number. So the real values can now be split across two different intervals. Okay. So now we have, as I said before, coming back to the robust region, we can still use the context of the robust region with the same definition as before, except now the preimage of this link function, by the way, this should be theta and no sigma, might be a union of two intervals instead of a full interval. And as long as we're in the robust region, because of the expression that I had before in terms of Chebychev polynomials, we're always going to have this fact that the asymptotic convergence rate is square root of the moment. Okay, so this fact that now the preimage of my link function can be two different intervals suggests to consider Hessians where the eigenvalues are not concentrated in a full interval, but where I can cluster them into two disjoint intervals. So that's what I'm going to do. Let's see where it takes us. So I'm going to consider that now my eigenvalues live in this set, which is a union of two disjoint intervals. And to make things a bit easier, I'm going to assume for now that these two intervals have the same size. Okay, so I'm showing a picture of what that could look like on the right-hand side. So this is, for example, the spectrum that you get off if you do least squares on MNIST. This is what the Hessian looks like. So you see you have an outlier eigenvalue, and then the bulk of eigenvalues is concentrated on the other side. So here, for example, you could take two disjoint intervals that include all the eigenvalues and still have a gap between both that is not zero. On some problems, not. On some problems, you might have a more kind of uniform distribution, and there might not be gap. But in this case, it turns out that there is a gap. So one quantity that's going to be important in the following is this capital letter R. That is the ratio between the gap, right, the size of the gap, and the length of the extremes. Okay, and so when R is equals to 0, that means that the gap is 0. When R is equals to 1, it basically means that all eigenvalues are concentrated at the extremes. So it gives us a measure of how distributed are the eigenvalues with respect to the edges of the largest interval. So although I write this through the theory, this assumption that the eigenvalues are distributed or clustered in different regions turns out to be verified in practice in some models. So for example, in deep learning, it's known that the eigenvalues tend to cluster like this in typically in like 3 regions where you have a lot of the eigenvalues close to 0 in the bulk. Then you have a sequence of eigenvalues that are detached from the bulk, and then much further away you have some outlier eigenvalues. Okay, so my next goal is, now that I have some assumptions that are different from the classical assumptions on the eigenvalues, I would like to find what is the optimal parameter, especially what is the momentum parameter, so I can get the convergence rate of the cyclical heavy ball method. Okay, so if I take, as I was doing before, the definition of robust region, and I try to minimize to find the M that is smallest but still contained in this robust region, I get this solution, okay, where the momentum parameter is given by quantities that depend on the ratio that I introduced before, and on this rho quantity that you can see it as the rate of convergence of gradient descent, for example. And I'm going to explain a bit more, give a better intuition of what this means. So although it's not as easy to interpret as the rate that we got for Polyak momentum, we can still say something about it. So one nice thing about it is that if you take r equals to 0, then we recover the rate of Polyak heavy ball. So that means that the cyclical heavy ball method, like if you take the optimal parameters and you don't have any gap, then you recover Polyak momentum, which is kind of expected because all this method should be optimal. Okay. The other thing to take away from this analysis is that this expression for the momentum term is decreasing in R. Okay, so what this means is that the bigger the R, the bigger the ratio, the smaller the convergence rate, so the faster you're going to go. So in other words, this rate is going to be strictly better than that of Polyak as long as the R is bigger than 0. So now that I said a bit about the momentum parameter, let's look at what happens for the step sizes. So the step sizes have a slightly nicer, or at least more interpretable formula. So the step size turn out to be 1 plus m divided by either L1 or mu2, which are the edges of the inner intervals. So L1 and mu2 are these two edges. So the largest and the smallest edge of both intervals. Okay. So again, if my gap is 0, this is just going to be this mu plus L divided by 2, and you recover classical heavy ball. But if not, these two step sizes are different. So what I'm illustrating here in the figure below is exactly that. What happens as I increase R? So when R is equal to 0, these two step sizes basically converge to the same point. If R is bigger than 0, getting closer to 1, then these two step sizes are very different. Okay, so here x-axis is one step size, y-axis is the other step size, and the color is the asymptotic rate, where darker means faster. Okay, so let's talk a bit more about the asymptotic rate. So as I said a couple of slides ago, the momentum term is the square of this, so the rate is square root of momentum. And this decreases in R. We don't really have a better expression for it in the general case, but we can look at it in specific cases, like for example, what happens for ill-conditioned problems where mu is much, much smaller than L. So in this case, we do have an asymptotic expansion for this that I think sheds some intuition on this. And in this regime, the convergence rate turns out to be the convergence rate of standard Polyak heavy ball times this term that is square root of 1 minus r squared, which is something smaller than 1 for any r that is greater than 0. Okay, so in other words, in this regime, which by the way, here on the right-hand side, I'm plotting both curves for condition number 0.5. So for any, which just means like the largest eigenvalue is 2 times the smallest one. So except for extremely well-conditioned problems, this approximation is quite good. And it says basically that compared to standard Polyak, what you gain with the cyclical step sizes is a factor of square root of 1 minus r squared. Okay, so of course, when r is closer to 1, this is a lot. When r is closer to 0, less of an improvement. Okay, so I'm going to talk a bit about the experiments that we did. So we compared standard heavy ball against this cyclical variant on, I think, 2 data sets, MNIST and synthetic, and also quadratic regression and logistic regression. So in the quadratic class, we basically get results that match the theory as expected, because here in the MNIST data set, we know that there's a gap in the eigenvalues. We know that we can find an R that's non-zero. In particular, I think in this case, R is 0.7. So there's a significant gain in the asymptotic rate. Slightly more surprising is the results on the logistic loss. So all that I said is, of course, valid only for quadratic objectives. Yet it seems that some of these results translate, at least empirically, to nonlinear problems like logistic regression. So what we did here is solve the problem first, then compute the Hessian at the optimum and take as parameters. So the smallest eigenvalue, largest one, the gap R, to be those of the Hessian at the optimum, and then run the method with these parameters. It's not really a practical way to solve a problem, but our goal was not really to be fast as one on logistic regression, but to see if any of these results kind of generalize to logistic regression. And with these parameters, it does seem like there's a significant speed up even for logistic regression problems. So the challenge here in logistic regression is, of course, that the spectrum changes throughout iterations. But even with that, it seems that the speed up is preserved. But of course, a lot more empirical validation and theoretical works need to be done to conclude something on nonlinear problems. Okay, so I'm reaching the end, and before I get to the conclusions, I would like just to say a few words on cycles of length larger than 2. So my talk was mostly about, I called it cyclical heavy ball, but it might as well be alternating heavy ball. I was just considering like step sizes that take 2 different values. But of course, you can think of generalizing to higher order cycles, like to take step sizes that take 3 different values and then start over, 4, etc. In the paper, we have more information about that. But so I just want to mention an intuitive way that we found to think about what's the optimal method for different step size lengths, which is the following. So we found out that for a method to be optimal, one thing that is sufficient is that this function that is 2 times the link function minus 1, so it's kind of a link function usually the link function between 0 and 1, but we're shifting, sorry, between -1 and 1, we're kind of shifting it to be between 0, sorry, it's between 0 and, okay, so this is, sorry, and we just need this expression. Forget what I said about link function being centered. It's just a affine function of the link function. So we need this thing to hit -1, 1 at the edges of the interval. Okay. So for example, if the interval being the interval where I have, or rather than interval, the set where I have my eigenvalues. So for example, if my set that has all my eigenvalues is just one interval, then a linear link function would do, because I can always find some function, some linear function that is +1 at one extreme and -1 at the other extreme. I don't need cycles of order 2 or 3 or 4. Okay. I now consider the case in which I have my eigenvalues live in two disjoint intervals. So in this case, if the two intervals are of the same size, I can find a quadratic function that hits +1 and -1 on both sides. And the linear function has no longer this property, because like if it hits +1 and -1 at the extremes, it's not going to hit +1 and -1 in the inner edges. You could construct a polynomial of degree 3, so a cycle of order 3 that does verify this property, but it's not necessary with cycles of. So in this case, it shows that if the eigenvalues of your Hessian belong to two intervals of the same size, there's no gain in going to higher cycles. Now, finally, suppose that we're in the case in which we have our eigenvalues lie in a union of two intervals, but both intervals are of different size. Okay. Then it's a polynomial. You cannot always find a polynomial of degree 2 that satisfies this property of being -1 + 1 at the edges, but you can find a polynomial of degree 3 with this property. So in this case, to find the optimal, you could get faster rate by going to schemes with 3 cycles. Okay. So let me recap a bit what I talked about. So the main takeaways are that the cyclical heavy ball, we can prove that it converges faster in the presence of a gap in the eigenvalues. And assuming we have knowledge of this gap, then we can set this parameters according to the largest eigenvalue, the smallest one on this gap. And with this element, we have a convergence rate that is roughly equal to the convergence of classical polyak heavy ball times a factor that is smaller than 1. Empirically, we've observed some speed up on non-quadratic objectives. Although the theory that we have is mostly limited to quadratic. In the paper, we have just local convergence on non-quadratics. But I still suspect a lot of these things could be extended to more general non-quadratic objectives. And finally, I want to mention some problems that we could not figure out in the paper that I think would be interesting for future work. So I briefly hinted it in the last slide that there are ways to deal with more general eigenvalue sets that are not necessarily the union of two intervals of the same size. However, even for the case of 3 cycles, we don't really have a way to find the optimal parameters. I think it's possible, but there's still some work to do on that. Another open problem that we have is that of interpolating step sizes. So one thing I didn't mention is that in the stochastic regime, the way a lot of people run this cyclical heavy ball method is not by alternating between 2 step sizes, but rather to take a linear interpolation between two step sizes, like on one epoch, you're going to start from one step size, and at the end of the epoch, you're going to reach the other step size. So in the full gradient, it will still default to the same method that we're using, but maybe there's some advantage in having a more gradual interpolation between two step sizes instead of just jumping between one or the other. Another problem is, how do we estimate this gap between the eigenvalues in practice? One way around it is to do a top k eigenvalue decomposition. That's feasible in some cases, but you never know like how many eigenvalues you're gonna have to compute before you can estimate reliably the gap. And I suspect there must be a simpler way to estimate the gap that doesn't involve exactly computing eigenvalues. Finally, all this that I mentioned is on full gradient algorithms. Of course, the stochastic regime would be an obvious thing to do next. Some of the issues is that we need to figure out a different proof technique, because the polynomial formalism only applies for full gradient quadratic methods. But I still think there's some research to do there. And finally, also, of course, generalization to non-quadratic objectives like logistic regression. We saw that empirically it works, but so far, I think there's a lot of work to do on theory. And that's all for me. Thanks a lot for your attention and for the invitation. And I'm happy to take any questions that you might have.
Okay, thank you very much. Please, questions? Yeah. Igor, please, you can ask your question.
Hi, Fabian. Thank you for a nice talk. I wanted to ask about the momentum parameter. Do you have like any idea whether it makes sense to apply a sort of similar trick like cyclical trick for the momentum parameter from theoretical or practical side?
Yeah, that's a good question. So we briefly considered it to also be able to cycle through the momentum parameter, but we found out that it didn't really lead to any gains in terms of convergence rate. Meaning that suppose, as we did, that you're allowed also for the momentum to be cyclical, and then you kind of optimize everything, you get the same rates. Like the optimal method is the same. So in terms of rate, you don't gain much. There still might be something to do in terms of robustness, like maybe setting a cyclical momentum helps somehow, because maybe the robust region is larger, so you have more choice of parameters that we haven't looked into. Yeah, and we also didn't. So this is true for 2 cycles. I honestly don't know what happens for larger cycles. Like maybe you could think of keeping 2 step sizes, like having a cycle of order 2 on the step sizes, but a larger cycle on the momentum parameter. I haven't checked that. In general, it seemed to me when we did the analysis that there was some like duality between the step size and the momentum parameter, that you could cycle one or the other and it was giving the same results, but for some reason it was not worth to do both at the same time. And we went for like choosing different parameters for the step size and not the momentum, just because it was I think what people were doing, at least in the papers, was on deep learning. They're usually doing cyclical, like they're doing the cyclical rate, like the cyclical choices between the step size and they're fixing the momentum.
Yeah, thank you. And I also wanted to ask, maybe I missed this, but how do the rates that you obtained like compare to Nesterov's accelerated gradient method? Yeah. And maybe also to like this method of conjugate gradient method.
Right. Yeah. So great questions both. for Nesterov, so in the quadratic case, Nesterov achieves the same rate as Polyak momentum. I mean, the advantage of Nesterov is that it works on non-quadratics. But here, since I'm focusing on quadratics, the rate is the same. So basically everything that I said for the rate of Polyak is the same for Nesterov. So the way this compares is that the rate that you would get is the same one as Nesterov, but multiplied by this term that depends on R that is, smaller than 1.
But can we say that the method that you presented is more robust to the parameter choice?
Yeah. By the way, I just realized when I said Nesterov now, I meant the linearly convergent variant of Nesterov, not the 1/t² variant. That we haven't checked, like whether we can get acceleration with similar assumptions, trying to achieve accelerated sublinear rate. We haven't looked into that, but that's a very interesting question. Yeah, and the other question was on conjugate gradient. That's a really good question. We didn't look at well, I mean, we haven't explicitly compared against conjugate gradient, but conjugate gradient being, it's kind of optimal in a slightly different sense, but still, like the worst case behavior is the same one as Polyak or Chebychev method. So you could say we haven't really argued that in the paper, but you could argue that one thing that this implies is that the conjugate gradient also would reach this, let's call it super accelerated rate, where you're achieving better rate than Polyak, because it adapts automatically to the, like without need to set a new parameter, it already adapts to the shape of your spectrum. So just, because this method needs to be strictly worse than the conjugate gradient, I think you can say that all conjugate gradient, you can, like you have an upper bound in the rate of convergence that's the same one as this one. So in other words, this shows that conjugate gradient can also get a rate larger than Polyak under these assumptions. Sorry, a rate like better than Polyak under these assumptions.
I see.
I don't know if that makes sense.
Yeah. I think it's clear.
Yeah. The reason why we didn't focus that much into conjugate gradient is because also the theory is mostly for quadratics. Kind of my interest is in methods that generalize to nonlinear objectives. And well, conjugate gradient also is great on quadratics. We know it doesn't really work that well on non-quadratic objectives. But I do think there might be something to do in deriving faster rates for conjugate gradient under this kind of assumptions, like having a gap in the eigenvalues.
Yeah, thank you.
Yeah,
thank you. Nikita, please, you can ask your question.
Fabian, thank you for a great talk. Have you tested such methods on special cases of non-convex problems, for example, weak convex problems, which typically arise in deep learning, where we have outer convex loss function, but we train, for example, a deep neural network on some compact. For example, we use some gradient clipping to make our space compact one, and finally achieve a weak convex objective. Do you expect some gains from cycling of step size?
Right. Yeah, thanks a lot for the question. That's very interesting and allows me to say something I forgot to say, is that the original works that propose doing cyclical learning rates on deep learning problems, they justified it precisely as a way to accelerate it on non-convex problem, because their intuition was that taking shorter and then larger step size will allow you to escape saddle points. That was their intuition. That was back in 2017. I think now we know a bit more. Maybe saddle points are not exactly the issue, which is one of the main motivations also to look into this problem on quadratics. We said, well, okay, if their intuition is wrong, or at least it's not the full story, what happens on a well-behaved problem like quadratic? Can we say something about the convergence in this case? Coming back to your question, so follow-up question I have for you, because you mentioned outer or inner. I'm assuming you're interested in it in the context of min-max problems. Is that correct?
It's one of such interesting problems.
I see.
The problems I'm interested in too, of course. So, are you delving in such direction?
Yeah, I'm not, but I think it's very interesting. Yeah, I honestly don't have an intuition besides the quadratic on why it should work on non-convex problems. Well, I mean, locally you would still get the same acceleration that we get, but outside of like non-locally at the beginning, I honestly don't know what would happen. You know, maybe the intuition of the original paper was right, and it also helps you.
As I guess we can gain some intuition by constructing convex auxiliary tasks. For example, by adding some regularization term, which can be, for example, added and subtracted, and we have another type of problems, difference of convex functions, which is also well studied, and sometimes just bringing up a weak convex problem, constructing a strong even convex problem from this weak convex problem. Which is really frequent in deep learning. We can gain some even acceleration, which is theoretically proven.
I see. Yeah. So yeah, you're thinking like, for example, catalyst-wise, like adding a strong convexity parameter, or wrapping everything into.
It's one of the ways. Yes, of course.
Right. Yeah. Yeah. So if you, trying to relate that to this, to the cyclical learning rates, one of the issues that's not clear to me is, well, if you add regularization, you're kind of shifting the whole spectrum. I wonder if there's a way to do that, but be a bit more fine-grained and not shift the whole spectrum, but maybe only part of the spectrum. So that you introduce a gap and then you're more effective in using different learning rates. But I guess that would require you to know something about not only the eigenvalues, but also the eigenvectors to know.
Yeah, it's a good hint, of course.
Yeah.
So I expect we can gain something from such ideas, I think, too.
Yeah. Yeah, one of the things I would be curious also in the non-convex regime is, or even in the non-strongly convex, is the choice of the step sizes. Because here in the strongly convex regime, you know, your step sizes always depend on largest eigenvalue, smallest eigenvalue. I think, and it doesn't really degenerate to anything useful in the convex regime. Like if I take this smallest eigenvalue mu go to 0, then I converge to the generic method, like with momentum 1, something like that. So I think a different analysis is required for the non-strongly convex regime. But I would be very interested to know, you know, what is the optimal momentum, what is the optimal step sizes in this case. As you hinted, it's probably going to be something similar to Nesterov. I haven't also tried to redo the Nesterov analysis with these assumptions of a spectral gap. I mean, first we need to figure out what is the reasonable generalization to the spectral gap on nonlinear problems, because now your Hessian is changing. So you need to be a bit careful on how you define it.
Oh, I think we have some clues on what can we do next by estimating the gap. We have inequalities which use L and mu terms for convex objectives. Its definition, it can be used as definition for a strong convex objective and objective, for example, with Lipschitz gradient.
Yeah.
So we have algorithms which can adaptively estimate L term, but I think we have some works. I can't relate to the precise work, but which also uses idea of inequality, which uses mu. But we can scale it iteratively and exponentially faster. It gave us some sufficient value to mu, which of course worse than knowing precisely mu and L.
Right.
But can speed up slightly, at least, our algorithm.
Right. Yeah, but to me the question is, can you do something similar, but for the gap, to estimate, not the largest or smallest eigenvalue, but also, the R parameter.
Yeah, it's still open question.
Exactly. Yeah.
But we can try from this idea second, I think, to gain something more reasonable.
Yeah, that's a good idea.
Thank you for your answers.
Thanks,
Thank you.
Nikita.
Thank you. Maybe another questions. Elnur, do you have questions?
Yeah, basically, I wanted to ask what was the idea behind this, as far as I understand, assumption on these two gaps, two intervals of eigenvalues. Was it taken empirically from, I don't know, you had these figures, or it was presumed somehow from theoretical part?
Yeah, that's a great question. So it came from theory, actually, and then we realized that it was verified empirically on some problems. So actually, I don't have a figure for it, but the first motivation that, the first hint we got that this gap was important was from the work on the field of orthogonal polynomials. So people that have looked into this orthogonal polynomials with varying coefficients have looked at, okay, what happens with orthogonal polynomials when they have this varying coefficient, and they knew that the zeros of this polynomial, they're not concentrated on an interval, which is the case of standard orthogonal polynomials with fixed coefficients. They already figured out that the zeros of this polynomial, they can be distributed in a union of two disjoint intervals. So basically, yeah, reading on this classical literature, this gave us the hint that might be important.
Okay.
And then the way we kind of presented in the paper is through this link function, which is the function that maps your eigenvalue, like the interval that contains the eigenvalues, to wherever the Chebychev polynomials are evaluated, hopefully in -1, 1. And we saw that, well, while classical, like the traditional one is always an affine function, the one using like two cyclical step sizes is this weird square root of a quadratic function, and this, the preimage of the -1, 1 interval, then in this case is kind of split on two intervals, so that that also kind of suggests that the reasonable thing to do is to look at to disjoint intervals.
Yeah, generally speaking, you say that, I mean, you refer to this classical work and to find the answer. I mean, I mean, generally to sum up, the answer is in these two papers of Chihara and Vanash.
Yeah.
Okay.
Yeah. By the way, yeah, and you cannot click on it, but I guess Alexander will put the slides online soon, and there's going to be the link there.
Yeah.
Maybe another quick question. You had this Hessian class again, well, classes on real data sets, and was it quadratic problems or logistic regression as well? So
right. So this is just quadratic problems. Well, okay. Several. So there's quadratic problems, there's logistic problems, and honestly, they look the same.
And where do you estimate the Hessian then to estimate?
Yeah, that's a good question. On logistic regression, I estimated at the optimum.
Okay.
Which, I mean, is not a practical thing to do, but since the results that we have are on local convergence, it seems to me to be the thing that was most reasonable to do given the theory that we have. I also tried it like at initialization, and it was still converging fine. But my guess is that that's going to depend a lot on the problem, you know, whether the spectrum changes a lot or it doesn't. Like that might work on logistic regression. It's definitely not going to work on something like deep neural networks, where at initialization you have a lot of, like, for example, negative eigenvalues.
Mm-hmm.
Yeah, and by the way, yeah, so the things I was showing before were on linear model. This is on, well, I don't remember which architecture, but it's on some deep learning architecture. Yeah, so here it's only at initialization, but in the paper there's also some plots at convergence where, like, the idea is the same, that you have a bulk, like some extremal ones, and then an outlier.
Okay.
Yeah. So for example, here you can see there's a clear gap between both that you might leverage. Maybe on the one on the top, it's less clear that you have a gap. Like in this one, for example, maybe it's better to have union of 3 intervals instead of 2. So yeah, I think different models will require, like, if you want to take full advantage of it, to have different cycles or different assumptions.
Okay, thank you.
Thanks.
Okay, thank you. Nikita, you have another question.
I just forgotten to contact lower hand. Yes.
Okay, I see. Okay, colleagues, thank you very much. Fabian, thank you very much for very nice talk. We have a big discussion.
Yeah, thanks a lot for all the questions.
Yeah, thank you very much. Thank you. And we periodically organize different events in Russia. Unfortunately, at the moment, it's not too simple, but I guess in future, we try to invite you to join us on some of the event, say summer school for young researcher. Okay.
I would like that.
Okay,
Thanks
thank you. Thank you very much.
Thank you.
Thank you.
Thanks.
Bye.